Hi everyone, I hope you're enjoying SQL Bits Virtual so far. My name's Darshna and I'm a lead data scientist at Elastacloud. Elastacloud are a data science and cloud consultancy. So thanks for joining my talk today on securing the future with AI. I hope you find it interesting. So what are the key takeaways from this talk? I'm hoping people can just get a general idea of some of the ways in which we can use data science and AI within digital security. So just to cover a brief agenda, I'm going to cover a bit of background information as to why threat prevention is growing increasingly complex. We will look over some of the challenges and processes that digital security teams use as well as hackers themselves. And then finally, we'll go through some demos and tools that are at the disposal of security teams and data scientists to enhance their security approaches. So why is threat prevention growing increasingly complex? Well, with continuous advancements across technology in every vertical, we're seeing exploding data volumes. It's not unusual for large organizations to collect 6 terabytes of security data per month. That's an enormous amount of security logs, monitoring various different entities, looking for various different vulnerabilities, which are constantly evolving and being added to each day. So that's challenge one within itself. Moving on, the network perimeter is essentially being dissolved with the advance of bring your own device policies to work. We're seeing smartphones, smartwatches, tablets, PCs, all adding to the volume of access points that can lead to data breaches and vulnerabilities. Without equally sophisticated security systems monitoring all of those devices, an organization can be left open to many different types of vulnerabilities. And then finally, with the introduction of new and improved data protection laws such as GDPR, we're seeing organizations faced with extremely steep financial penalties as a result of data breaches, and this also leads to deep brand and customer trust effects. All in all, the rewards for attackers are exacerbated. So how are digital security teams typically structured? So most organizations will have a digital security team, but the structure is likely to vary depending on the organization size, the security need, and the organizational priority. But if we look at a typical security team structure, you would typically have a chief information security officer to which 4 distinct teams feed into. So initially you have the incident response team, which consists of the security operations center, who are continuously monitoring for various different vulnerabilities and managing them adequately. You have the offensive engineering team, which generally consists of penetration testers who are trying to find new ways to infiltrate existing systems, also evaluating current and new security tools and products. Then we have the project management office, who in terms of coordination will liaise with legal departments around existing security incidents, and in terms of administration will ensure all teams and personnel within an organisation are adequately trained to ensure they're conducting their day-to-day business in the most secure way possible. And then finally we have the risk management team, who will carry out various different scans across all their entities to ensure the risk to data breaches and other vulnerabilities are minimised. So what are some of the ways in which security teams are mitigating against security incidents? Well, they may implement multi-factor authentication, role-based access controls, patch operating, configure macros, conduct daily backups, and a whole host of other different types of activity. Various different security frameworks do exist, but they all follow a general kind of goal in order to mitigate against security risks, which initially follows identifying threats and protecting them, putting in processes to protect against those threats. Where that's not possible, we need to ensure we have systems that are looking out for potential vulnerabilities and detecting them so that we can respond quickly and recover and mitigate the damage done by various different incidents. So data science is often regarded as the silver bullet within cybersecurity. Unfortunately, it won't be, as we are continuously coming up with new and improved ways to protect against various different instances. Likewise, different attackers are creating more and more sophisticated infiltration approaches and systems. So whilst data science won't be the silver bullet within security, it does provide security teams with a much more proactive approach to managing incidences rather than reactive, which has historically been the approach. So rather than waiting for an incident to occur and then tracing back the activity that preceded that event, we now have an automated system that is highlighting anomalous activity, and then you have a window of opportunity to minimize that damage by shutting down systems or blocking user activity and things like that. So whilst we can implement various different data science approaches within security, it's not without its challenges. As I mentioned, we're dealing with terabytes, sometimes petabytes of data. And while we do have big data tools such as Azure Databricks, it's still a large challenge within itself, particularly given the incidence of security events is quite low. Secondly, we have the lack of labels. So as I mentioned, historically, digital security has been quite a reactive approach. So after an incident has occurred, we may get a label and then look into the build-up to that event, if there was one at all. Nowadays, on the dark web, attackers are getting their hands on zero-day type software, which can lead to that kind of build-up to an event, essentially invisible. And then we have false positives. So this is more in the realm of anomaly detection. So whilst we may be monitoring all of the activity going through our networks, we are looking for events that happen on a much more smaller scale. They are less likely to occur. You're not looking at distributions of 50% of your activity is anomalous versus the other 50% is normal. This is incidence of 1%, if that. So with that, all of our models are generally, traditional models will suffer from a high false positive rate, which can overburden security teams if they have to manage a lot of different vulnerabilities all at the same time. So just to cover a little bit of the history of how AI has evolved within security. In the early 1990s, we had rule-based anomaly detection. So this is your traditional rule-based approach, where you're not really capturing the dynamic activity that may precede an event occurring. As we continued to advance in technology, we got data mining based approaches. So this saw the introduction of security information management systems, essentially large data lakes that are combining all of your security data sources in one place. So whereas previously we may have rule-based anomaly detection on a few data sets, all occurring independently of each other, now we have a much more synchronous, holistic view of all of the different types of activity going on from a security point of view, and we can mine that data to find anomalous patterns. As big data tools continued to advance, we started to use machine learning based anomaly detection. So here we saw the introduction of deep learning approaches, which were kind of really sophisticated in the sense that you could implement models which would in real time identify malware and then more recently, we've moved to a complete new paradigm shift with deception-triggered data science. And the idea behind this is, rather than continuously monitoring your data for anomalous activity, you are creating high-fidelity events, potentially using generative adversarial networks, such as Malgan, which is a generative adversarial network which produces malware. And then you can correlate your activity to the activity of the high fidelity event. So rather than looking for a needle in a haystack, you have a much more definitive field of search, which is much more manageable. So in terms of data science approaches to security, in the literature you will often see it debated whether supervised or unsupervised techniques can produce the best results. It kind of depends on the organisation and where they are within their security journey. If you have a lot of history and know the kind of events that you're exposed to, a supervised learning model may be of use. And here are some of the kind of key algorithms that are used for anomalous signature detection and just general anomaly detection. So we have seen more recently, as I mentioned, the introduction of unsupervised deep learning methods or semi-supervised models, and they seem to be really innovative and produce some interesting results in a research kind of scenario. But it is really interesting to see how or whether these models perform in real life in different organisations. So as the saying goes, with great power comes great responsibility. So we've considered some of the ways in which security teams are using data science and machine learning to enhance their approaches to security. But I just want to briefly cover some of the ways in which attackers are also using AI. So there are various different papers on how attackers may potentially use AI. One of them is PASCAN. So this was discussed at NIPS more recently. So just to cover the general architecture of a generative adversarial network, you essentially have two neural networks competing against each other. And the analogy that's often associated with explaining GANs is that of the forger and the detector, or the authority figure. So the generator in this example, say we had a forger that was trying to create fake banknotes, and he or she would have some real data which gave them key features as to how to create a real fake note, or make it seem like it was a fake note, and that would be mixed in with some noise. And it is the job of the discriminator, which essentially acts as your binary classifier, in trying to identify whether the sample presented by the generator is real or fake. The idea being, with fine-tuning and iterative learning steps, you can essentially get the discriminator to effectively distinguish between real and fake banknotes. So just going back to the example of PASCAN, this was a GANs model that was trained on 9.9 million leaked unique passwords. And it was found to be twice as effective at cracking passwords as John the Ripper's Spider Lab rule set, and as competitive with Hashcat. So that GANs network was able to understand some of the human patterns behind creating passwords, whereas John the Ripper's lab rule set was much more of a definitive rule set. So it must have maybe a few numbers, a few special characters, etc., etc. In addition to cracking more passwords than this rule set, it was able to augment the results of Hashcat. So when you use them together, it was able to crack 200,000 more passwords than when Hashcat was used by itself. So just to go through a few more examples, we have SnapR, which is a social network automated phishing tool. A lot of people obviously share a lot of information on social media, whether it being Twitter, Facebook, Instagram, etc. So this particular tool would basically capture a lot of personal information to tailor tweets specifically for individuals with malicious links. And on a platform like Twitter, where it's quite often to shorten the URL, people are less likely to inspect it in as much detail and are quite easily tricked into clicking on malicious links. And then just to look at some inference type hacking as well. So this is where infiltrators are trying to gain information about how machine learning models are used, whether it be they make an API request of some sort and try and decipher what type of information a machine learning model is using in order to trick it and feed it wrong information to bypass a particular protective system in order to gain more information or bring down systems, etc. So some of the kind of real life examples this can apply to is the transport industry. So many transport systems across the world are autonomous. The DLR, for example, within London is predominantly autonomous, and these type of inference hacking systems can trick autonomous vehicles into misinterpreting stop signs or speed limits, which can be detrimental and extremely dangerous. Additionally, we have in the sector of retail the ability to bypass facial recognition when using ATMs or phones. And then within finance, a lot of banks and financial institutions will put in anomaly fraud detection systems based on your location, etc., and your spending habits and things like that. So if somebody knows the kind of features that go into those autonomous machine learning models for anomaly detection, they can essentially increase the chance of a false negative being detected and infiltrate a system to commit fraud, espionage, or sabotage. So where to start? There are many different types of security incidents. The top 10 are kind of listed here. So we've got denial of service, phishing attacks, insider threats, eavesdropping attacks, SQL injection attacks, birthday attacks, malware attacks, many, all of which have many different variations. If you're new to security, it can be quite overwhelming to kind of understand exactly how all of these can occur. I would recommend, if you are new to a security team or are trying to enhance security efforts with data science in a security team, it's often useful to ask questions that can point you in the right direction rather than trying to take it all in at once. Just try and understand what are the type of attacks that are seen most frequently within an organisation. They will be quite different. Larger organisations, insider threats might be much more prominent than phishing attacks, where they may have implemented really robust training schemes to prevent that from happening. So it's always good to ask those kind of questions. What type of attacks do you see the most? What preventative methods do you have in place? What data is being collected to monitor whether incidents occur? Those kind of things. So if you know a particular organisation is particularly vulnerable to a certain type of threat, your the quality or the impact you can make with data science will obviously be targeted towards that kind of area, so you can try and improve or augment any security processes that already exist. So in addition to trying to take in all of the different types of incidents, there are also many different security products that will already exist in a very saturated field. So a security information management system aims to collect different data, store it, give you the ability to investigate it, support mitigation and report on security data, so you can put in place adequate incident management processes to minimize the damage against those risks. So every year Gartner put together a report on all the different SIEM offerings, which is kind of displayed here, and they're evaluated in terms of whether they are a challenger, a leader, a visionary, or a niche player. So Gartner assess these different SIEM offerings in terms of support, the functionality, does it provide analytics, is it scalable, what are the additional features, how well does it integrate with your existing systems, is it value for money, what other features does it provide. So this is an interesting read, just to kind of get an idea of some of the products that are available within the security space. But one particular SIEM I'm going to spend a bit of time talking about today is Azure Sentinel. So this is Microsoft's SIEM offering and is leveraged decades of their security experience. So it provides you with the ability to collect multiple data sources all in one space. As you would with your data lake, you can collect data from AD logs, on-prem, various different clouds. If you're thinking of doing a SIEM migration, you can also collect all of the data from your parallel SIEM using Ceph and syslogs. It provides you with the ability to detect threats with its inbuilt AI, providing you dashboards that are kind of ranked in terms of risk factor. So you have a much more managed and organised approach to detecting various threats. You can also implement and use their templated playbooks or build on those playbooks to continuously monitor for various different threats as well. It gives you kind of really nice hunting tools with KQL to constantly query and look for various different threats, as well as a graphing tool. So some of the threats that are identified in their dashboard, you can see how that was highlighted as a threat. And then you can put in place different remediation processes with logic apps to block user accounts or turn off VMs, etc., etc. So one of the key selling points of Azure Sentinel is the alert fatigue reduction. So it has state-of-the-art scalable ML algorithms which are correlating those anomalous events to present security incidents that are known in the data. So where we have this typical issue where security teams are overloaded with the amount of vulnerabilities they need to assess and manage, this inbuilt AI allows you just to focus on a few of those cases, so reducing that fatigue that you see across security teams. As well as using their inbuilt AI, you have the ability to develop your own models as well. So as I mentioned, you can bring in various different logs into Azure Sentinel, query them using log analytics, but you can also develop your own custom models using Azure Databricks or Azure Machine Learning Service, which is what we're going to cover in the demos. And then using logic apps and event hubs, you can feed that back through to log analytics to give you that much more customizable view as well. So we're going to cover two demos today. I've been using the KDD dataset, so we'll be predicting specifically denial of service attacks in Azure ML. and then using Databricks too. So just a bit of background about the KDD 1999 cup set. It is rather old, quite outdated, and probably does not reflect a lot of the robust infiltration techniques and approaches that are often seen today. But as you can imagine, kind of synthetic data sets with security type instances are fairly rare to get your hands on. So I'm going to use this anyway, and we'll speak about some of the kind of drawbacks of using this data set as we go along. So this was a data set generated by Lincoln Labs, set up in an environment to collect 9 weeks worth of raw TCP data, and it simulated a typical Air Force local area network, but they peppered it with multiple attacks. So the raw data consists of about 4 gigabytes compressed, and the training data is about 7 weeks, which consists about 5 million records, and the test data yielded around 2 million records. So they didn't put the various different types of attacks within this data set, but they didn't put the same type of attacks in training and in testing. So it kind of simulates reality in a much more balanced way. So the data set consists of 41 features. And we have various different types of attacks that can be grouped into predominantly 4 different categories, with denial of service, unauthorized type attacks, and probing type attacks as well. We've got 9 basic features which tell you things about the TCP connections themselves in terms of duration, the protocol type, the number of source bytes and destination bytes, and whether it was flagged for an error status in the connection or not. And then we have content features, which are domain-based knowledge. So it tells you things like the number of failed logins, whether it's a guest login or not, the number of outbound command line sessions, etc. And then we have traffic-based features. So these are your lag-based features, which are basically using a 2-second window to count the number of connections made previously, and look at the number of connections to the same service in the current connection or in the past 2 seconds. Okay, so demo 1, building a predictive security model on Azure ML. So once you're in the portal, you just want to search for machine learning, and you'll be able to, I already have one created, you'll be able to add a Azure Machine Learning workspace. So just select your subscription and your resource group, or create a new one if you don't have one. Give it a name and select the region you'd like to have the workspace in. I would recommend using the enterprise version because it does give you the full functionality of the really nice interactive GUI that Microsoft have for managing everything from your data to your models to deployment. So yeah, that's a great tool. So if I just go back to the one I've created, so you can manage a lot of things from the portal within itself. I would recommend downloading the JSON configuration if you want to use local compute rather than cloud compute for initial experimentation. Otherwise, you can go ahead and launch the Azure ML Studio, which has a really nice friendly interface. So you can author notebooks, you can use the drag and drop kind of functionality just to get some basic kind of insights, or try and see how some initial models will run. If your data set's fairly clean or small, it's a really great tool, but you can also do some of the pre-cleaning and featureization in there too. You can add data sets within the workspace. You can manage all of your experiments, pipelines, models, and even test some of your endpoints once you've deployed your models. You can manage all of your compute, so you can have compute instances and compute clusters, more for experimentation and development of models. Your inference clusters, more for deployment. And then you can attach compute, so if you want to integrate your Databricks cluster here, you can attach them here too. You've got your data stores. So when you create your Azure Machine Learning Service workspace, you'll be kind of given a whole host of other kind of resources. So as well as the workspace, you also get a blob storage account, Key Vault, and application insights. So when you do experiment and deploy your models, you can understand a bit more about errors and logs there as well. And then obviously when you start deploying and experimenting, you've got your container registry there too. So the first demo I'm going to show is just basically using some of the drag and drop functionality, the auto ML functionality, just to get an initial insight. So as I mentioned, if your data is fairly clean, perhaps some of your engineers have already done some pre-processing, you can get some really basic, quick initial runs to have a look at how a predictive model may perform. And then the second part of this demo will show how you can use Azure ML in a much more traditional kind of notebook format, where you are kind of configuring all of those different hyperparameters as well. So if we just look, if you want to create a new auto ML run, you just need to add your dataset in. So I have two here, but you can easily create one and you can upload them from local files, your data store, web files, or your open dataset. So I'm going to use the blob storage just as an example. We're going to import some of the correlation data that I've already looked at, and it is tabular. So then you just go on next, you select the blob container that you would like to browse from. So mine's called KDD. We want to select the correlations and then just hit next. So here you can get some initial kind of view of what your data looks like. You can see that it's not using the first row for the column headers, but that can easily be changed. And you can tell it if you want to skip rows or anything like that. You just confirm the schema that all the data types are correct, and then just hit next. And then you just confirm all of the details, and you can create your data set, and then it's there. So you just select your data set and then hit next. So actually, let's go back and use this one. So you just give your experiment a new name. You have to select the target column, which we want to identify if connections are denial of service type connections or just normal connections. You need to select a compute cluster. I don't have anything running at the moment, so I'm just going to cancel that and show you one of the ones that I did before. So this one ran for 2 hours and 9 minutes, but you can set different parameters on that. So if you want to cancel your run after an hour or after your experiment reaches a certain level of accuracy, you can do that too. So if we go into this, you can get some details about the run itself, best summary of the best performing models. And then if you go into models, you can see a few more details about that. So some of these are probably likely to have overfit. You don't really want accuracy of 100%. But if we look at this one, So they've applied different normalization techniques across standard algorithms like SVM, but you can look at all the other metrics as well as accuracy. So if you wanted to use your weighted AUC, you can see that too. So that's a great tool for kind of getting started with some initial kind of understanding of how a security machine learning model may perform. But if you want to, if you're working in a larger team and you want to kind of make things a bit more configurable, maybe try a few more advanced algorithms, you can use notebooks. So if you go ahead, you can either create an environment or on your local PC, or you can create one using some of the Azure ML functionality. So go ahead, open your Jupyter notebooks. I've just imported all the packages I need, and you can do everything here. So you connect to your workspace, you mount your data store. I've just read it in the key kind of data set I'm looking at, which is the 10% of the KDD set, and I take that tabular file and make it pandas data frame, and I can see here all the 42 different columns with all the features that I need to try and predict denial of service attacks. So I did mention that the training data consists of a few million rows, as does the test set. But initially I was training this model using local compute, so I just took a sample of that data. And then I went on to look at what are the distributions of the different types of activity in this data set. So I can see normal activity consists of 87,831 different connections. And then the next anomalous type activity is almost half that. So this isn't very realistic. In the real world, you're probably going to have a lot of normal activity and the odd anomalous type connection. So I've gone on to filter this, so it's on a much more representative scale. So we've got around 1% anomalous activity in comparison to this 50-50 kind of view that we have here. And I've filtered just to look at the denial of service type attacks. So just a bit of information on the denial of service attacks. So denial of service attacks generally overwhelm a system's resources so that it can't respond to service requests. And distributed denial of service, which is more commonly seen today, is just that on a much more scalable level using various different VMs. So you can get different types of denial of service attacks as well. So you've got volumetric type attacks. So in this type of attack, the attacker continuously sends huge amounts of packets with the purpose of saturating the network's bandwidth of the target. You've got protocol attacks, and in this instance, the attacker consumes all of the victim's resources, such as the processing capacity, the firewall memory, and so on. And then finally, you've got application attacks, which in this form of attack, the attacker is continuously sending HTTP requests to bring the web server to crash. So I have sampled the Neptune attacks to sit from 57,000 to about 1,584, and then taken the remaining denial of service attacks with the normal activity as well. So that's the data set we're now looking at, and then I've gone on to explore that a little bit further. So we can do some exploration to look at the general distributions of those different kind of columns, check for any outliers, things like that. And then we can check things like the protocol type. So we can see most of them are TCP followed by UDP and ICMP. We can look at that across the different types of activity too, and we can look at various other different things. I've then gone on to create a binary classifier feature. So we're not looking at every single type of denial of service. We want to kind of make it a much more generic denial of service model. So anything that is normal activity is classified as 0, and if it's anything other than normal, then we classify it as 1. And we can see the distribution of that new filtered data set now. So we've got 87,000 normal connections and only 3,695 denial of service type connections. So we drop the type and then just check the schema of the remaining features. We want most of them to be of numeric, so these categorical variables either need to be changed or dropped. And then finally we've gone on to do some correlations. So I've done some point visceral correlations here, and we can see, as expected with denial of service attacks, that a lot of those lag features where we're counting the number of connections in the previous 2 seconds to the same host, to the same service, are significantly contributing to the predictability of whether a connection type is anomalous or not. And that's just represented there in a visual format, which is a bit more appealing. But we have confidence that the features represented in our data set are indicative of different types of activity, be it normal or denial of service. So then I've now done my exploration. I'm confident that this is a good data set to start with. We can create an experiment. So I've just defined my training file here. So imported all the relevant packages, initiated a run context, split my data into training and testing, just done a very simple logistic regression, and I've logged the accuracy and the AUC, and then we've saved that file out as a pickle file. So to run the experiment, we need to first create a compute cluster. So you can do this using local compute, as I mentioned. Here I have created a compute cluster. So it is called SQL bits, and if it doesn't exist, then the cluster will be created. And then we've gone on to define our environment as well. So using Azure ML's kind of configurable environment initiation is much more easier than, well, I found is much easier than trying to kind of create your own environments and having to deal with Docker and all of the kind of complexities around that. So this is very simple. You just define the environment and then you put it all together in an estimator. So you define the compute target, the environment, and your entry script, and you can watch the progression of the run using run details. So you can see that was completed yesterday at around 11 PM, and I have the accuracy and the AUC there. But I can also go into the into Azure Machine Learning Studio and see the output of that. So if I go into experiments and click on KDD training, I can see all the different runs, many fails, 2 completed runs, and we can see the accuracy. If you decide to change hyperparameters using the regularization rate, you can see that how accuracy changes with that as well. So if I wanted to go on to, so you can change lots of different things within each run. So this might be interesting if you're doing something like a neural net and there's a lot more parameters that you can kind of tune. You may want to look at how that affects the model performance overall, and this is a great tool to see that. So if I want to go into a specific run, I can get some details about how long the run took, the initial kind of metrics. So here it's got a great accuracy, but much more reliably, the AUC is much lower, indicating that 1% anomaly instance is obviously highly imbalanced, leading to the kind of bias within the model where it's much more likely to predict all connections as normal, even though they aren't. So you probably want to adjust that probability default from 0.5 to kind of account for that. You might even do some kind of resampling with smote and things like that, depending on how imbalanced your data is. So that brings us to the end of how we can use Azure ML. You can deploy a model quite easily once you're happy with your experiment. So Microsoft have given us great resources which you can clone the GitHub repo, and you've got all the notebooks here from getting started to dealing with different types of compute, creating pipelines, deploying a model, if you want to do batch inferencing or tuning hyperparameters, even if you're scared of or concerned that your model is biased in any way, you can use some features of the FairLearn package, which allows you to correct for that to some degree, which is really good. So that's Azure ML. The other thing I wanted to kind of briefly talk about was Azure Databricks. So as I mentioned, you can develop and deploy models and integrate it with Azure Sentinel quite easily. And depending on your preference, I guess, you can use either. There are many various different articles around comparing Azure ML versus Databricks on various different parameters such as cost, efficiency, etc. Working within security for a little while, we generally have a preference to use Azure Databricks, predominantly because of the volume of data we're dealing with and the interactivity between different teams. So it's likely that you're going to have an engineering team that are landing the data and processing it to some degree, and they're probably going to be using Scala on Azure Databricks, but you'll also have BI teams and even security analysts who are much more familiar with languages like SQL and KQL. So it's interactive for data scientists, but also on a much wider scale in terms of interacting with other types of teams too. So just to show that you can create the same model using Azure Databricks, I will just take you through the notebook. So you just create your cluster as usual. I've imported all of the data sets directly here, but you can again link to various different data sources, whether it be data lake, blob storage, etc. So I've imported all of the kind of packages that we need. Again, we can see the data that we're dealing with, all of the different features there. We can carry out the same basic cleaning and understanding how much data we're dealing with, the different distributions of connection types. We can do the same sampling of the Neptune type attacks connections. So once we've filtered all of those denial of service type connections with the normal ones, again, we can classify that into a binary column. So here we're just seeing the distribution of normal to DOS type connections on a visual basis. So here we've created our binary column where everything that is normal is classified as 0, otherwise we classify everything else as the denial of service type connection. We go on to do the correlations as we previously did, and then we can model using various different algorithms. So I've just dropped all the categorical variables here. So we vectorize everything, do our test train split. I've applied a GBT classifier in this instance, and then we can make predictions on our test set and evaluate that. So we've got the F1 score of 0.99. This ranges from about 0 to 1, with anything closer to 1 being it performs quite well, and anything less than about 0.7 probably needs a bit more refinement. So the F1 score is kind of gives you an indication of precision and recall, but you can also output a confusion matrix quite easily. So with this run, we can actually see, interestingly, it didn't make any false positives, but it did make false negatives, 21 of them. So this is where it's predicted that the connection type was normal, but it actually wasn't. So again, you probably want to kind of adjust the probability default there, because in a security kind of incident, you don't want to miss any incidences, but you don't mind so much managing some false positives, as long as that's on a manageable level. So in implementing this in a security instance, would probably want to adjust that a bit more. You can visually look at the results too. So yeah, that brings me to the end of the demo for the Azure Databricks part. As I mentioned, you can probably deploy these models, creating some scoring notebooks, and manage that using Azure Data Factory, which can then be linked and fed those results back into Azure Sentinel. So you've got that holistic view in Azure Sentinel of your automated AI that Microsoft bring, but also some of the custom models you can hash together as well, based on like all of the different data sources you have available. So just to conclude, we have looked at why threat prevention is growing increasingly complex, some of the challenges faced by digital security teams. We've also looked at some of the data science approaches used by security teams as well as hackers. And then we've gone on to explore some of the critical questions we can ask within security settings, as well as how we can potentially design and experiment with different data science approaches and even deploy models, feeding back into Azure Sentinel to give security teams that really holistic picture of their security environment. So that's my Twitter handle. If you have any questions, feel free to reach out. I will also make all of the code available on my GitHub as well. Thank you very much.